In Chapter 4.6, we're going to make sense of the mathematical solution of the 2D heat transfer equation by visualizing the solutions. We'll have a look at slices through the slab so that we can vary one parameter whilst holding the other constant. Then we'll have a look at heat maps as a way to visualize how both parameters affect the temperature profile in the slab. We'll begin to consider the solution by calculating the constants of integration for a series of index values. So I'm going to use Excel to do this, and in column A I have the index values n, and in column B I'm going to calculate the constants of integration using the formula that we just computed from our solution. So if I propagate that through, what we notice is that every other constant of integration is zero valued, and that makes sense because if we scroll back to our definition of what this constant of integration is, it basically says that every time m is even, we have 1 minus 1 in the numerator, which goes to 0. So we can actually use this fact to save time. We'll only bother calculating the odd index terms in our series solution. Welcome back to Igor Pro, where we're going to be visualizing some of these solutions for our heat equation. So here's the slab we were looking at before. This time it's a little bit transparent, so you can see internal bits, but our hot side is just where it was before, and all the other sides are either insulated or cool. So what we know is that all the variations are going to be in this xz plane. So one way to start looking at this is to hold one of these parameters constant and let the other vary, and that enables us to make a two-dimensional plot, like just a normal graph. So I'm going to add this surface in here at the position of z equals 0.5. And so this is the surface I'm interested in looking at. And I'm going to take a slice through that by holding z constant and letting x vary in the solution. You'll remember that y does not contribute any dependence to this heat transfer equation. So I'm just going to neglect the y-axis because it doesn't add, the slices along the y-axis don't add new value to the problem. So we're only going to look at the x dependence. Okay, so what I want to do is plot the temperature profile along that x slice. All right, so for a position zeta fixed at 0.5, I've chosen to use just one term in the series, which is obviously not correct, but just to see how it looks. And I'm plotting my temperature profile as a function of this x-related coordinate c. All right, so that's just the first term in the series. If I want to plot a solution with two terms, I'm actually going to have to go up to the index 3 because you remember all the even indices are zero valued. So we want to go up to the third index. So if we include that additional term, the profile changes a little bit. It's certainly apparent, but the one-term solution was not so far away from the two-term solution. All right, looking good. Let's add one more term to our series solution. So we'll add the fifth term because, again, only odd terms have a non-zero value. And if we do that, we see that there's almost no difference between the index 5 term and the index 3 term, which suggests that actually you don't need a whole lot of terms at this particular z value to get an accurate solution. So I'm just going to expand the curves here, and you see that yes, the n equals 3 and n equals 5 solutions are still overlapping very well. Does that mean that we only need, n equals 3 or n equals 5 terms in the solution? Probably, but that will depend upon the sensitivity of the solution that you need. So if you need something accurate to like many decimal places, it's worthwhile going and checking how much these two curves are actually varying. But for most intents and purposes, I would guess that just calculating the first n equals 1, 3, and 5 terms is good enough. Okay, we're back with our slab, and now we're going to take another slice at a z position that's a little bit closer to the hot surface. And again, the hot surface is at z equals L, which in non-dimensional coordinates is zeta equals 1. And so we know that as we get closer to a hot surface, the temperature changes more rapidly, and so the form of our solution, it generally needs more terms to be accurate. So let's define a slice that's 90% of the way towards that hot surface. So that's going to be the cut we take when we make these two-dimensional plots. And then we'll go ahead and evaluate how the temperature profile changes along the x direction at zeta equal to 0.9. So we'll start with just the first term, and that gives us a solution that looks very much like the solution we had at the midpoint, zeta equal to 0.5, except that in this case, the non-dimensional temperature is much higher because we're closer, again, to that hot interface. Okay, so let's add the next term in this series, considering an index of 3. And all of a sudden, you get an answer that's a little bit surprising, and it is actually aphysical. The true heat transfer profile does not have a dip in it like this. So what's wrong? Well, the only thing that's wrong is that we're not considering enough terms in the solution, because it really is the superposition of each of these terms added together that gives an accurate profile for the temperature. So let's add the next term in the series and see if it starts to converge on something. Whew, no. We'll add one more. Maybe it's starting to move less. I'm going to jump straight up to 21 terms. It's starting to level out a bit more. We're not seeing that sort of sinusoidal up and down. So that's a good sign that we're getting close. I'm going to jump now, another jump straight up to 101 terms. And it's still changing. It would probably take, maybe another 50 terms to get a solution that isn't changing rapidly. But we're starting to see this like broadened shape of the curve that's going to be the true physical temperature profile at this position in space where we've taken a slice 90% of the way along the z-axis. And again, the reason why this profile changes so much for low index values is that the point in space is close to a temperature gradient. And so whenever we have a large temperature gradient, the summation solution is going to require more terms to get at what I would call a stable solution, one in which consecutive index terms are not changing significantly. Okay, now let's try taking a slice in the opposite direction. So we're going to hold C constant at 0.5 and see how the temperature profile is affected by the z-coordinate. And what we will note here is that because one edge of this slice is touching a hot side of the surface and another edge is touching the cold side of the surface, we'll expect probably a monotonic change in temperature where it increases as we increase the z-coordinate. We'll also expect that the side of the profile closer to the hot temperature is going to change a lot more with the number of terms that we compute. All right, so we'll go ahead and we'll start with our first term in this series. And as expected, the temperature rises as we approach the hot surface. So we'll jump straight ahead and look at 5 terms. And there's a significant difference at the side closest to the hot temperature, closest to zeta equals 1. But at the lower values, where zeta is closer to 0, there's not much change between the profiles whatsoever. All right, so we'll add a couple more terms. And the slope starts to turn over, so it looks like we might have a change in curvature. But I'm just going to jump straight ahead to 100 terms. Still different from the previous trace. Let's just double check that we're getting close to a final solution. So we'll go to 200 terms, and we see that things are not changing between 101 terms and 201 terms. So basically, somewhere between 11 and 100 terms is where the effect of adding terms saturates, and we get, a reasonably accurate solution. We can finally visualize our heat transfer solution in 2 dimensions. And to do this, we're going to use a heat map. So we're going to vary both the x and z coordinates, which in our case are xc and zeta. And for each position in this slab, we're going to calculate the non-dimensional temperature. And so what that actually looks like is a matrix of values. And here we have all of our different xc values, and along the columns we have the different zeta values. And so for each spatial pixel, if you will, we're computing the temperature. And then rather than plotting that as a number, we plot that as a color. And that's what this color mapping is showing, is that a non-dimensional temperature of 0 is dark, and a non-dimensional temperature of 1 or 1.2 is yellow. The reason that our non-dimensional temperature is allowed to go above 1 is that some of the series solutions, let's say the 21st term, has a temperature value that's slightly above 1, but it's added to a whole bunch of other solutions that have values slightly below 1, and so on average, when you sum all the solutions that you need to get an accurate response, you won't have a temperature that's above 1. If you were to plot a temperature above 1, that would be an indication that you haven't calculated enough terms in the solution. Okay, so that's how a heat map works. Now let's look at the heat map for just one term in the series solution. As expected, this position zeta equals 1 is the hot plane, and so we see heat conducting, and it's kind of radially conducting away from this hot plane. And the reason is that these two sides, where xc equals 0 and xc equals 1, are both at a cooler temperature, and so the center is going to be the hottest point. We notice that this solution is going to be symmetric about xc equals 0.5. So if we were concerned about computational effort, we would only calculate 1/2 of the solution and then reflect it over the axis, because there's no need to duplicate the calculations on both sides of this line xc equals 0.5. Okay, so we've considered one term. Now let's add another term to our solution. What you're seeing are the summation of a sinusoid that's not being modulated by other sums. So you're seeing those two distinct, almost like eyeballs popping out, because the two terms are both contributing strongly to the solution, and where they're similar valued, it looks like the solution, the temperature is more even, but where the two solutions, the n equals 1 and the n equals 3 separate solutions, are very different from one another, you get these intense gradients in temperature, which are aphysical. It's just an indication to us that we haven't computed enough terms in the solution. So we'll add another term, and we get another eyeball in the solution. And again, this is just, we're summing overlapping sine curves, and there's not enough sine curves to make a smooth solution. So we're seeing the spikiness of the sinusoids. Again, we add another term, we get another eyeball, but you can see that they're starting to smear together a little bit. So we'll jump ahead and we'll go to 21 terms, and you get a lot more hot spots, but they're starting to merge. We'll go up to 101 terms, and it's looking a lot smoother, but you can still see on that top row of pixels that we've chosen that there are aphysical inconsistencies because there shouldn't be hot spots. The back plane is isothermal, so it should be uniform. So finally I went up to 201 terms, and that's when the solution converged on something that is physically meaningful. And what you'll note here is that, especially at these corners where the boundary condition of T1 equals the boundary condition of T2, we're actually getting that T1 plotted correctly. And so that's a good sign that our solution is involving enough terms to be accurate. If we look at this, and we'll assume that this is the correct solution, I have no better one, it's exactly what we expect. The hot source is radiating radially into the cold 2D slab.